Hello everyone, I'm Hongtao from Harbin Institute of Technology. It's my honor to give a presentation here. The title of my paper is Satellite Starting Beam Scheduling Strategy Based on Multi-Agent Reinforcement Learning. Now I will talk about the paper from following 5 parts: Introduction, System Model, Multi-Agent DeepQ Learning, Simulation Results, and Conclusion. The first is the introduction. Low Earth orbit satellites are an important part of space-air-ground integrated networks. With the large-scale deployment of OneWeb, Starlink, Telesat, and other mega-constellations, LEO satellite shows its advantages in reducing communication delay, providing wide area coverage, and not affected by the ground environment. However, due to the high mobility of LEO satellites, terminals need to switch frequently to maintain the connection of communication links. This will increase the signal overhead and drop call rate of the system, and seriously affect the system throughput. With the development of phased array technology, many satellites begin to use starving beam technology. So, how to balance the load of each satellite and meet the communication needs of hotspots is an important problem to be considered. In this paper, the satellite starving beam scheduling problem is transformed into a two-dimensional mode, and we propose a novel satellite beam scheduling strategy based on multi-agent reinforcement learning that aims to maximize the system performance. This paper, we consider the problem of LEO satellite beam scheduling during satellite operation as shown in Figure 1. Every satellite is equipped with a multi-beam phased array antenna system, so it can gaze at one or more hotspots by adjusting the parameters of antenna array. And the Earth's surface is divided into a fixed number of hotspots. Figure 1 shows the coverage of 2 orbiting satellites to the hotspot area on the ground. The yellow dotted line is the satellite orbit. From T1 to T2, Area A is within the coverage of Area 1, so Area 1 can adjust the antenna to maintain the connection to Area A. At T3, Area 1 exceeds the visible range of Area A and starts to serve Area F. In order to simplify the model, we use a two-dimensional plane model to model the starving beam scheduling problem, as shown in Figure 2. A series of hotspots, that is the red spots in the figure, are evenly distributed in the plane area. The satellite, that is the blue dot in the figure, moves along the fixed orbit, that is the yellow dotted line in the figure, at the same speed. When the satellite moves beyond the plane area, it will appear from the other side of the map and continue to move along the track. Each satellite can provide starving service for one or more regions at the same time, which is constrained by the maximal number of beams and the elevation angle between the satellite and the starving region. And each region can also accept the service of multiple satellites. When the satellite serves a hotspot area, this paper assumes that the satellite can completely cover this area to avoid the discussion of incomplete beam coverage. When dealing with the starving beam scheduling, there are 3 main factors considered in this paper. Satellites should provide service to the nearest hotspots as far as possible to improve the service quality. When the satellite moves out of a hotspot area, other satellites should continue to cover the area to reduce the drop rate of the area. The satellite load capacity and the capacity of the hotspot area should be considered in beam scheduling. If the satellite capacity is not enough to fully serve the current region, other nearby satellites should participate in the service to ensure the service quality. Suppose there are M satellites and N hotspots. We can get the weight matrix W, the beam allocation matrix F, the capacity allocation matrix C. In this paper, incomplete service rate, handover rate, and insufficient capacity rate are used to measure the performance of beam allocation. Incomplete service rate (PB) refers to the proportion of hotspot area whose business requirements can't be met. Handover rate (PH) is used to measure the frequency of satellite switching hotspots in the service process. PC is the insufficient capacity rate of hotspot area demand, which is a supplement to PB. Then, the starving beam scheduling problem can be regarded as an optimal problem. Here, alpha 1, alpha 2, and alpha 3 are positive parameters. The first restriction means that the number of beams allocated to hotspots can't exceed the total beams of the satellite. The second restriction means that the capacity allocated to hotspots can't exceed the total capacity of the satellite. It is an NP-hard problem, so we try to use reinforcement learning to solve the problem. DeepQ Learning algorithm is a classic and effective reinforcement learning algorithm, which can solve complex problems in many communication scenarios. We extend the DeepQ Learning to multi-agent case to solve the problem of starving beam scheduling. In the multi-agent DeepQ model, the learning and the decision of each agent are realized by DeepQ algorithm. The align Q function fitted by neural network and the objective Q function are randomly initialized, with the continuous interaction between the agent and the environment. The generated action sequence is stored in the experience pool. The multi-agent DeepQ learning algorithm is shown in algorithm 1. In our algorithm, the reward can be expressed as above. And here the first item is the distance penalty. The second item is the disconnection penalty, and the last item is the connection reward. And A is the penalty coefficient of disconnection, and B is the reward coefficient of connection. We should find the best value A and B to get the better performance. Then we set a simulation scenarios, and the simulation parameters are summarized in the table. We consider a square area within 500 kilometers set length, where hotspot areas are randomly distributed within the area, with the number and the capacity of satellites are fixed. We focus on the impact of the maximum number of beams and the number of hotspots and the algorithm performance. In terms of satellite capacity, the satellite capacity is set to 3 Gbps, and the maximum capacity demand of hotspot area is 1 Gbps. First, we compared the effect of penalty coefficient A of disconnection and the reward coefficient B of connection on the beam scheduling performance. Figure 3 is the performance of the system varies with the penalty coefficient A of disconnection. We can find that when A equals 1, the handover rate is the lowest. Also, the rate of incomplete service and the insufficient capacity rate at a low value. Figure 4 is the performance of the system varies with the reward coefficient B of connection. From the results, B equals 0.75 can get a better performance. So we set A equals 1 and B equals 0.75 in next simulation. Then we realized the multi-agent DeepQ learning algorithm and get some results. Figure 5 shows the influence of the number of beams of satellite on the handover rate, incomplete service rate, insufficient capacity rate. With the increase of the maximal number of beams, the performance of KM algorithm and multi-agent DeepQ algorithm is improved. When the number of beams is small, the performance of KM algorithm is better than that of multi-agent DeepQ algorithm. However, with the increase of the number of beams, their coverage performance is almost the same, but the multi-agent DeepQ is significantly better than KM algorithm in the handover rate. This is because the punishment of satellite switching is strengthened in the training, so the satellite connection strategy is adjusted. Figure 6 shows the influence of the number of hotspot error on the handover rate, incomplete service rate, and insufficient capacity rate. As the number of hotspots increased, the performance of both algorithms decreased. The handover rate of multi-agent DeepQ algorithm is always better than that of KM algorithm, but its coverage performance is not as good as KM. In general, by adjusting the reward setting, the reinforcement learning algorithm achieves better performance in handover rate. In the future, when the number of satellites is increasing, the coverage performance will not be the main consideration, while reducing the handover rate can greatly reduce the signaling overhead of the SIM, which indicates that multi-agent DeepQ algorithm is a desirable starring beam scheduling algorithm. Finally, we draw the conclusions. In this paper, we have investigated the starring beam scheduling problem in LEO satellite network. By establishing a two-dimensional model, an optimal problem is proposed under the constraints of the number of satellite beams and satellite capacity. We have solved the problem by multi-agent DeepQ learning algorithm. Simulation results have shown that the proposed algorithm can reduce the handover rate, which is of great significance to reduce the network signaling overhead. In the future, we will continue to pay attention to the beam allocation of LEO satellites. The follow-up work can consider using real spatial data for simulation analysis and integrated the traditional beam scheduling algorithm and reinforcement learning beam scheduling algorithm according to different application scenarios to obtain better performance. My presentation is over. Thank you for listening.